We're live. Go.
Hi, I'm Mark Millis. For those who don't know me, I led NASA's Breakthrough Propulsion Physics project from around 1995 to about 2002 while it was funded. And then I was allowed to keep working on it on center overhead for another 5 years until 2007. And that project looked at such things like faster than light flight, non-rocket space drives, the kind of things where the physics is still incomplete. I took an early retirement from NASA in 2010 to continue working on such things and under a nonprofit called Tau Zero Foundation. And one of the things we did in the Tau Zero Foundation was create a book about comparing the desired science fiction flight that we see and the unfinished physics where there might be rooms for future discovery. And recently, last couple of years ago, I resigned from the foundation that I quit, and I am presently working on an interstellar, on a grant with NASA to create a catalog of interstellar propulsion methods. And the talk that I'm giving today is about the deliberate use of science fiction to aim you into the beginnings of science. And I cover it from a few different angles. And the actual charts are from a class that I gave at a university in Dresden, Germany for a couple of times. So with that, I will go ahead and get started. I figure this is as good a quote as any way to start out, that it's so easy in the course of doing normal work to just extrapolate what you know or stay within the realm of what you don't know. But to make breakthroughs, you have to go into the unknown. Hello? And one thing for sure about the science fiction, and this is a book from 1982. There's plenty of books on this subject, but this one in particular looked at all of the rocketry pioneers and asked and tried to see what the inspirations were of science fiction. All of them, without exception, were inspired by the science fiction of their day. But because they're inspirational does not mean that it's instructive or that it's unfolding. And the example that's often given, the Jules Verne, is that, well, yes, they did launch from a peninsula. Yes, there were 3 people aboard on very similar things to Apollo. But here's some huge differences. Instead of a cannon, it was a rocket. But the one that really struck me the most is that when it happened for real, the entire world got to watch on TV, or everyone across the world had a TV. And that's kind of a big deal. And that impact of that kind of thing in a fiction story would have been full. So that was a huge thing that was not in the science fiction. I thought I would share just a little short snippet of the fiction that inspired some of contemporary rocketry. And that was the kind of fiction that inspired this.
4, 3, 2, 1. Booster ignition and liftoff of Space Shuttle Endeavour, preparing our home.
Okay, and I'll just go from there. Now, the one thing you might notice is there was kind of a much bigger plume on the real thing. It was not built by a lone inventor, and this is not able to reach other planets. So the mismatch again from the fiction and the other, but it was definitely inspiring. And one way to kind of look at that transition is that back in before the Apollo era, the major fiction that was inspiring was those things like the serials of I can't remember their names now. Flash Gordon, Buck Rogers. The idea was, well, at least get into space, and the idea of putting people on the moon was like the central icon. And the presumed method was rockets, to take rockets from this idea that had been kind of not fully developed into something we could use. And we succeeded. And now the generation that I grew up, the idea is to reach for other Earth-like worlds. And the presumed method, since rockets are pretty much at the limit of the capacity they could do for doing interplanetary stuff, is figure out how to control gravity or go fast in the light. So we had a completely different fiction. And I'm going to skip playing this fiction of the starship going to warp drive. I'm sure this audience has seen that plenty of times. So it's been long enough from that. What do these visions look like that we have now? Actually, we don't have any. We're not at that point yet. What we do have is some physics for doing traversable wormholes or warp drives. And I'm not going to, and if you later in the questions, if you want to go back into these, I can. And actually, the traversable wormholes was inspired by science fiction. Longer story on that, but to get to the point, when it comes to science fiction, what's the big deal? Well, the stories pull us into why we want those gadgets and which gadgets would be the really cool ones to have. The novelty can break us from familiar and break us from that thinking of just doing extrapolation. The one that I found particularly useful is the images that they provide in the fiction become like a visual backdrop or things that you can use for thought experiments, so you don't have to devote some of the mental energy to that aspect while you play with these things in your mind. And then the last one, the logical inconsistencies or even the errors that they make or whatever, they're not necessarily bad things. They can pull in deep questions about trying to figure out, well, what's going on. So those can be actual useful to provoke reasoning. Okay. I'm going to use the Star Trek as an example and what these things imply. Obviously the ship can go faster than light, which implied some sort of physics for that, which is kind of a no-brainer. But the other aspects is that they can move the spacecraft around without needing rockets. They can deflect incoming objects, and they have some synthetic gravity for the crew. All of that implies some control over inertia or gravitational forces for which we do not have the science yet. And then there's a bunch of other things like ample energy and power and weapons and things like that that I won't necessarily go on, but they're part of the picture. One thing that I've learned over the years, if the science fiction inspires, don't pursue the specific idea in the fiction. Look at what the goal was rather than how they did it. So in other words, if the warp drives inspired you, don't try and make a warp drive. Try and think of any way that you can go faster than light. And instead of thinking of inertial dampers or anti-gravity or those sort of things, think of as many possible ways of manipulating gravitational forces or whatever. And with this, the ones that I find most useful is coming up with as many different approaches as you can, rather not just one, but in many different ones, and then distill those down into their critical issues and unknown. And I'm going to expand on that one with some examples. And for fun, these are some of my own inspirations growing up. And all of these, in particular, the aspect of the inspiration was that these spacecraft could levitate. Just that feat itself of being able to levitate was inspiring. And when I have a live audience, I often like to query for a show of hands, how many recognize all of those vehicles? And there's a few in there that are a little obscure, but come back to that maybe. Okay, so now we're going to do some fun science fiction. We'll start with this particular one here that is, you should all know, the Landspeeder. And so, okay, what's holding it up? How's it levitating? And what are the consequences of things that he ran over, like if he was to run over a frog? But here's the one that starts to get you into some of the, you notice when it's parked, it just doesn't kind of drift off to the side. I mean, there's nothing holding it down. So what is it? What magic is keeping it from moving laterally? And also anchors it very firmly. So there must be some substantial force producing magic that can keep it from moving laterally. And well, if that was, then why would you need the jet engines on it for pushing it laterally? You just use that magic to move the craft in the direction that you wanted. So those are some fun things you can start to mess with. And then the other thing you can start to mess with is questions like, okay, well, if it ran over stuff, what would happen? And how big of an obstacle is going to make it need to maneuver or whatever? These things can begin to pull you into deeper questions for fun. Here's another one. If For example, the device worked by shielding gravity. If he parked under a Ferris wheel, in which case the part that he was parked under would have no gravitational forces, and the part that he was not did. And so the Ferris wheel would begin spinning up faster and faster and faster. What would really be the consequences of that? Um, the other one, and this is the one that happened to me when I was a kid, somewhere between 10 to 14 years old. And this was my favorite vehicle. And so, if you want to ask from the point of view of a prepubescent teen, what vehicle would they have? Oh, well, a panel van that you can fly anywhere and that has sensors to look for interesting life. But what I would do is in my head, I would imagine it hovering over my driveway, and then I would throw rocks at it and poke it with a stick to try and come up with ideas for how it might be levitating and ask, if the rocks did something different. I'll just give some examples of that. Okay, for this first one, let's assume that the rocks, you throw them and there's no modification to our trajectory. That can imply that somehow that vehicle has no mass. It's almost like it doesn't even exist. In which case, well, what if I poked it with a stick? If it has no mass, would it have no inertial mass? In which case, it'd be very easy to move. Okay. So, what about if somehow it eliminated gravitation just around the vehicle? What would happen to the rocks? Well, the trajectories would be altered. When they were in that realm, they would quit arcing in the gravitational field and they'd go straight. And so that would give you another clue is that, oh, if that's what happens to the rocks, that might be how it's levitating. And then what if you threw the rocks and they all collected on top? Well, that would imply that it's using some sort of inverted gravitational field that is, in other words, the craft is falling up a certain bit as much as it's falling down and holding levitation. And then the last one in this series is what if it's some magical way of pushing downward on the space around it or the objects, in which case the rocks would be deflected downward. So these sort of mental exercises are fun to play in the fiction. And what was great is that uh, with that shuttle, I didn't have to imagine that. I could put all my attention on doing these various things. And then started thinking about, well, where do those forces come from? How could that be? And one of the things that pops out of this is um, gravitation on the Earth is clearly pulling it down, but gravitation from all the other masses in the universe are also tugging on the ship, but they're all canceling out. And to what degree is that influencing the physics right there where that is? And as I learned later in physics, that's tied to something called Mach's principle and inertial frames, which I won't really go into quite yet, but it begins to bring you questions about what else would we have to know? Um, I also wondered about, well, how much power does it really take to do that? Is this something that is really energy intensive or not so much? And so just did a couple of quick calculations, not so quick. It took me a while to actually, learn the physics and how to do it. But for the cost of electricity, it would only cost about $2 per kilogram and this is an idealistic case and one example. So there's lots of caveats that this might be totally bogus, but at least to put it in the ballpark of only about $2 per kilogram to be able to levitate that. Well, that's not much at all. It's not like creating a warp drive, which is an enormous amount of energy. Or to use an analogy for a copter, it only takes about 20 watts of power to levitate 1 kilogram, assuming the rotors are 1 meter in diameter. So we're not talking about enormous amounts of energy. So if we can discover the physics, we might actually be able to power something like this. So then let's start thinking about possibilities. And coming back to the Star Wars movie. And I remember when I first saw the movie, and this was before you found out later what these vehicles will do. And I was worried about, well, they parked it near a cliff and would it just drift its way off and fall off? Again, that whole issue of what's holding it laterally in place. So let's look at some of the possibilities. Well, one, what if it just crashed? It goes over the cliff and then falls down. That's one clue. What if it falls, but when it gets near the ground, it starts with some repulsion and doesn't crash? Or what if it just went straight? Those would mean different things. The first one would mean that, okay, there's some sort of a repulsion against the ground, but it's not a very fast or strong effect. and couldn't stop it from crashing. The yellow line is, well, it works and it is a strong effect, so eventually it will keep it from crashing. Or the last one, it uses something entirely different to levitate that has nothing to do with repulsing on the ground. Let's take that a little bit further with analogies. And this is where it begins to branch into the more interesting questions. Okay, how many ways do we know that things actually levitate? We have buoyancy, like hot air balloons or helium balloons and dirigibles. We have reaction force, like a helicopter that is pushing the air down to keep it up. And then we have ground effects, where the forces are between the vehicle and what's immediately underneath it. So let's extend these analogies, say, to gravitation. And this is just thought experiments that you can do to ask yourself, starting with analogy and working into things. So one analogy for buoyancy is that it totally cancels out the gravitation of the vehicle. Okay, let's say that's one. Another one is that instead of canceling out the gravitational mass of the vehicle, what if it cancels out the gravitational forces of the space surrounding the vehicle? Okay, another idea. Or what if there's some anti-gravity force where there is a opposite field applied to cancel out the gravitational one? And just a short segue here, my earlier point about coming up with as many different ideas as possible, this is a good point because the term anti-gravity, which has been used loosely to encompass this goal of levitation in general, it's only one of several possibilities. And if all you do is think in that term, you're limiting yourself. So the idea of coming up with as many possible variations on a theme gives you other things to explore. Okay, reaction force. Let's say it's doing force fields on the surrounding air to keep it up, much like a helicopter. But what about on space-time itself? If you could push on space-time itself, and for the ground effects, well, what about shielding gravity, like I alluded to when the Landspeeder parked under a Ferris wheel? And what if it had some way of repulsing it against the ground? Okay, so that's enough ideas. Maybe if I work harder, I can come up with more. So we have, what's that? 1, 2, 3, 4, 5, 6, 7 different ideas. So if 6 of them turn out to be a dead end, I've still got something I can work with. So let's now go to secondary consequences of that. If I zero out the gravitational mass of the vehicle, does that mean its inertia also goes to zero? And then you can start asking the consequences. And if you're negating the gravitational field of the surrounding space, a normal second question might be, well, how far do you need that effect to extend? And what might that look like? How much does it fall off? If you had the anti-gravity effect, would that mean that debris would collect on top? There would be a divot above the spacecraft where would essentially be the new falling point for everything. The helicopter analogy, well, is it just going to affect the air or about other objects? And then again, how far does the effect extend or need to extend? And with the pushing on space-time itself, what's the reaction mass? In the Newton's second law, for every action, there's an equal and opposite reaction. And also the third one, conservation of momentum. The way the rockets work is when you push out propellant in one direction, it pushes the spacecraft in the other. So the total momentum is zero, just the way it started out, as much going that way as going that way. So if you're going to magically levitate a spacecraft or push, what are you pushing on? And does space-time itself have something that you can push against? Okay, about the shielding gravity, how far does that effect extend? And are there other consequences because of that? Like the Ferris wheel analogy, which implies that energy is being transferred. And if you're repulsing the ground, what happens over water? Does it have to be a rigid effect to work or not? Now, what these questions give you is kind of a starting point for going to the next level of detail, to start asking, well, what would I have to study in physics to begin exploring this a little bit deeper? And I'm going to take a short segue about considering gravitation itself. And I don't know if I can get the animations to work on this. Nope, apparently not. I had a scene from Apollo 13 in there, which shows how things float around in space, the free fall conditions. And I had a scene from 2001 where they use a rotating cylinder to provide artificial gravity by the acceleration that you feel while you're going around. Those are absolute, genuine physics of gravitation as we know it. When you're in free fall, all the other objects are falling. And what was cool is my generation was the first generation that actually got to see what that would actually look like. Imagine in Newton's time, even to try and imagine how much imagination just for the picture to create something floating around. We're here, we could just watch it on TV and to see what it really looked like without having to come up with anything and without making any errant guesses. So that was a huge thing. So this is some clues about how what we do know about gravity. And so let's go to the fictional gravity. And instead of artificial gravity, which the rotating one, I'm going to use the term synthetic gravity, meaning some magical ability in your corridor on a spaceship to create gravitation, which, by the way, if we could do that, that would be a huge deal. Okay, so let's say we have an intruder alert and we don't like that. So, what if we turn up the intensity of the field so much that we squash them? Okay. Or what if we change the direction of the field to confuse him? Or for more fun, what if we just switch the fields around all over the place and bounce them around the walls to bang them up and disorient them? And as much fun as that sounds, here's the part where it starts to overlap with the next physics questions. These three, the intensity of the field, the direction of the field, and the oscillating one, we have magnitude, direction, and time rate of change, which are things that for each of those, there are equation elements that you can start to bring in, and you can start to ponder what would an equation for this look like, and that you would have to have all of those features in them, not just the intensity, but direction and also time rate of change, turning it on and off. Trying to create such things will help you realize what other physics you need to go learn or how you might perhaps approach the problem. Okay. And so that's where we now take the step into the first method of the scientific process, or defining the problem. And in the context of these breakthrough propulsion ideas, there's plenty of physics right now that is working to try and understand the cosmos in general, the birth and fate of the universe, the expansion or whatever. But when you look at those same phenomenon, the apparent dark matter, dark energy, quantum fluctuations, when you look at that from the point of view of space travel, you form different questions. And from there, how you go about collecting that data and looking at it is different. So that first step of the scientific method, where you're defining the problem, if you do that in the context of the breakthrough you're seeking, it helps point what comes next for the rest of the scientific method, collecting data, then forming your hypotheses, testing them, and learning from the trial and error. I'm not going to go into full detail of this chart, but this was something from a colleague about using science fiction to help identify what are the critical questions that we need to figure out if we wanted to do breakthrough spaceflight. And what that ended up translating into is a philosophy kind of like this. On the one side, you have the physics that we know, the rigorous foundations, the stuff that there's been enough checks on that we can pretty much rely on it being at least accurate to a point, if not totally accurate. Then there's the goal-driven visions, the faster than light, the synthetic gravity for the crew, the being able to propel spacecraft without using rockets, all those things. And with those, what are the critical issues and unknowns? And those kind of exercises that I went through before, if you zero out the gravitational mass, would that zero out the inertia? If you were to push on space-time, could it be a reaction mass? If a levitating mass is not only being pulled by the gravitation of the planet, but of all the other mass in the universe, and granted, those all cancel out, otherwise it would move. how do those things come into play there? And those are kind of like starting points. And then on the other side is that even though there's a lot of physics that is rock solid, there are things that we still don't know, and things where there's limits. We still don't know how to combine the larger general relativity, the smaller quantum vacuum physics, and where those unsolved problems overlap with the critical issues. That's stuff you can study, because if we haven't figured it out yet, there's room for future discovery there. And if it's important to get the breakthrough, then it's relevant. And that, by the way, was one of the tactics I used in the NASA program to help identify what you would actually work on. So just a little refresh here. Science fiction is inspirational, but not necessarily accurate or instructive. And to remember that as a distinction. And if you want to play in this, focus on the goal that you want to achieve, not necessarily how they did it in that particular fiction. And it's best to come up with as many devices as possible or a variety of ways of doing it. And then from that, start to play and understand what it is you know and you don't know, and what you need to go learn more about. Um, and with that, and I might actually have some time to go into it. I didn't know if I would get there. But then there's converting those things into equations, playing with the equations and seeing what they tell you. But basically, as you distill down on this, the best you can, the thing that you can certainly do, succeed at, is getting to the first step of the scientific method of defining the problem well enough, of what characteristics would your breakthrough device have to help guide you into what physics you would need to study more. And then from there, what hypotheses and things you could do. The and definitely build on the established knowledge, and also on what are the dangling loose ends that we haven't figured out yet. Okay. Okay, I do have time for them. So I'm going to go through some examples of ideas of this concept. I don't know how many of you have ever heard of negative mass propulsion. The idea is that if you had a mass whose sign on its gravitational attraction, gravitational source, inertia, if all those things were a minus sign, and you put a piece of that next to a positive mass, it turns out they would both accelerate in the same direction. It appears to violate conservation of momentum, but it doesn't. The momentum of that original system was zero. The sum of the masses was zero. And more detailed studies, assuming, well, if you didn't start with even masses, or if there were springs between them, what would be the consequences? It turns out that there's no physics violated, but we have no idea whether negative mass can exist. The critical feature of that whole scenario, though, is negative inertia, that when you push on a negative mass, it wants to go opposite to the direction you're pushing it. And that's what leads to all those things. This has been studied in various contexts, and it's kind of an interesting notion. And there are some physics research that's done looking for evidence of either indirect or direct negative mass or negative inertia things. Nothing really revolutionary discovered yet, but there's some provocative things in there. Okay, here's another kind of cartoon to get into another analogy. What if magically we could induce forces on surrounding matter, like I said before with the helicopter analogy or whatever, and we extend that to the entirety of space-time, or the entirety of our universe? And so you turn on your engines and your spacecraft moves one way and the rest of the universe moves the rest of the way. And for those who are already more alert, the big question is, what did the universe move relative to if it's the entirety of the universe? And dig deeper into that, you would get into unfinished physics, where conservation of momentum, the definitions of inertial frames and things like that are still, well, unsolved problems. Okay, here's another analogy. I don't know how many of you might have done this before in your uh, home playfulness, but if you put something on water, just anything to float, and you took some detergent behind it, that object goes scurrying off. It's called the soap boat. And so let's just do that metaphorically here. What had happened is the soap changed the surface tension of the water, and those asymmetric forces on the water propelled the craft. The water was the reaction mass. Now, we can use this again, taking analogies and stretching it into space time. Well, could space time be a reaction mass analogous to the water? And can we do local and asymmetric changes on space time? And then that asks, well, what are the various properties of space time that we can even consider manipulating? And those things over here, there's the stress energy tensor, gravitational scalar potential, Planck's constant, speed of light, quantum vacuum fluctuation energy, and perhaps other things. So there's a number of phenomena that you can begin to look at and ask, can I create an asymmetric field? And if so, what are the consequences? I'm not going to go into this one in detail, but starting to ask those questions, you can start to create equations for that, and then derive certain basic concepts or consistencies. Like if that whole idea of pushing against the surrounding space were viable, you could get a greater force if you could reach more space, or if whatever you're pushing at has a greater mass density, it's more reaction mass, or if you could impart a greater change in momentum between yourself and whatever that stuff was. So this kind of points you in directions to what to look for. Of course, there's plenty other things you need to dive into, but these get you into the starting points for where you can dig deeper. These are just some other analogies. Yeah, actually, that is probably the essence of, and I'm going to stop sharing my screen, of the, and go back to, there we go, of the essence of evolving from a science fiction idea into the beginnings of science. Use it playfully to understand what you do know and don't know. Get that to set your problem statement of what it is you're trying to solve more exactly. And from there, learn what is the known physics and the unknown physics, and see if you can find any new discoveries that will get you some ground. And with that, I will gladly open it up to questions. And if there are no questions, I do have another set of charts, which I think I have some more. Let me check those on a different. Okay. Oh, okay, great. The $2 per kilogram for what time period? That would be infinite. The analogy that I used is how much energy does it take to move an object from the surface of the Earth all the way out to infinity? It doesn't say how long it takes to do that, but that amount of energy, and it's not really all that much. I think it's so many megajoules per kilogram, which isn't a great deal of energy. So you would put that into it once, and from thereafter, your spacecraft would be buoyant, or hypothetically so. Okay, the other one of the issues of using fictional images, what is known is there's a resulting suboptimal reaction limited form behavior. Oh, okay. Yeah. Yeah. The question is that, we have our own biases of the things that we know or we think we know, and how they creep into other things. And the example given in the comment is when you have spacecraft banking in the vacuum of space, where you don't need to do that because there's no air for your um, aerodynamic surfaces to work on. Oh, okay. Well, here's another one too. And this is something that bugs me on a few movies. I've seen ones where they have, spacecraft in either orbit or in the middle of space, and the spacecraft will tilt for whatever reason, and they show the people all sliding down. And it's like, well, wait a minute. If you're in orbit and you're in the middle of space and you have synthetic gravity on your crew, it doesn't matter what position you're going to be in. The crew's always going to see this is up, and that sliding is, it's just, oh my gosh. And to make those kind of assumptions that the physics behaves out there as it does familiar to our analogies is something that can mislead you. um, I guess something worth sharing on that, it's a little bit broader than this, but when I encounter situations of huge unknowns, I'll use the example of ghosts. What I do to avoid getting into a limited bias is I simultaneously entertain conflicting hypotheses. All the way to that, okay, ghosts are dead people trying to communicate, all the way to it's a psychological phenomenon that's only inside the heads of the people, and a number of different things in between. And try and consider those openly all at the same time. Then, as evidence washes over me, and depending upon the reliability of the evidence, I see which of those hypotheses it might be consistent with. And over time, to see which of those hypotheses start to have more evidence to back them up, and then begin to lead you to some sort of guess or conclusion. Or better yet, to begin to contrast what would be an experiment or a critical question you want to ask to tell the difference between one hypothesis from another. And that can lead you into things. And I use that fairly generally to avoid getting biased. And biases, the way they creep in, confirmation bias, it is so natural and so typical, and often so hard to even notice in yourself that you're doing it. So, in line with the question, those things we think we know and how they might bias our thinking. Yes, that's a trap of human perception that we have to be aware of and try and work around. And that's where the science fiction is also powerful. If some author has extended beyond that and shown us a world where things behave differently, and given that image to us that we can play with in our brain, and understand. And some other typical examples that made me think a lot as a kid is when you had different time rates of change for different universes. There was a wasn't a Twilight Zone, an Outer Limits episode where a pilot crashes and he discovers that his time rate, everyone around him looks like they're frozen, but they're not. They're just moving much, much slower than him. And then there was a Star Trek episode where Captain Kirk gets hyper accelerated so he can move around quickly, and the rest of his crew is moving around slow. And those sort of contrast worlds that happen at different time rates can evoke thoughts. And even though we presumably know that can't happen, it becomes a fun thing for thought and can help expand our imagination into areas to get past that barrier of thinking we know things. The HAL, on the they make a model kit of that, and the model kit comes with the LED. And if you have any skills at all with model building, it's a really easy kit to come up with. Probably the hardest thing is masking it off for spray painting. Um, if you do HAL 9000 model kit, you will find it. I don't remember how expensive the kit. It's not outrageous, but it's not cheap either. I think you can find them on Amazon, and it is scaled to the actual show one. So that's a 1-to-1 scale rendering. And for other props, I made myself my own neuralizer. use the camera flash and things like that. I'm also a hobbyist who likes to build things. And maybe for a fun moment, you will remember this as a talk of science fiction methods. And in your subconscious, I've planted the seeds of breakthroughs that you will discover in your future. But you'll just remember this as a science fiction talk. Okay, I will give my email address to the conference organizers. I got into a situation back when I was with NASA that the amount of email I got was overwhelming, and I don't want to just make my email address too readily available because of that. I got burned that way before. But I will pass that along. So, especially if there are teachers who want to teach this stuff and want to get in touch with me on that, I will be happy to share some of my materials. If by chance you work at a university, I have a short course on interstellar flight and propulsion physics. It's about 10 hours worth of class material. So it's not, I mean, that's total presentation. I've given it at the Technical University of Dresden twice and at Purdue once. And it's a rather, well, I say superficial. I mean, I do go into some equations and stuff like that, but it's meant more for an introduction to the whole process, the options for interstellar flight. And then if you want to consider into undiscovered physics, what are some of those options, or what are some of the dead ends that we know about? What are some advice for how to proceed without misleading yourself and making a fool of yourself? Yeah, you're welcome. Um, that whole idea of finding analogies is probably the easiest way to get your foot in the door of something. And for the fast and the light, that's a whole nother one that you can branch out to. If you've never heard of Cherenkov radiation, look that up. That's how light speed in material objects, if an electron or whatever moves faster than the speed of light in that material, it will give off radiation that's called Cherenkov radiation. There's been no known violations in pure vacuum, um, but that's and another cool thing is just weird natural phenomenon. I'm not sure how many of you have seen this before. Let's see if I can pull it off using this analogy. And there's still some liquid in this, so this is going to be tricky. If I were to rotate this cup one rotation, it's not in the same state it was before. I either have to unrotate it or continue rotating it around a whole nother revolution before it is in its same state. One of the examples of this, and apparently someone said they did this physically, even though it sounds daunting, is if you have a cube and each corner of the cube ties to the corner of a room, and you rotate the cube once, you can't untangle the strings. If you rotate the cube twice or unrotate it, either way, then you can untangle the strings. This example is using the arm. Now, since the arm has no pivots on it, it's a good representation of I forget the term, a coordinate transform where you don't just have free rotation. Let's see, I'm going to have to get back. If I rotate my arm around possibly the way, okay, now this, by virtue of the location of the handle, you'll see that it has done one rotation, but clearly my arm is not in the same position it was before. And if I unrotate it, okay, that's one way of getting it back. But the other cool thing, if I keep rotating it around, I'm not sure that fit in the view, but then it comes back to its same state. And that's a weird thing in physics. It's thought to come into play with parity, but a single rotation of an object is not the same state. You have to do two full rotations before an object ends up back into some state. And there's just something so cool about that. Okay, what are the edges of science that seem most promising for space travel? The unfinished physics of, and it goes by a number of phrases, and I'll try and remember all of them. There's something called Mach's principle, and there's something called inertial induction. And okay, let me, before I explain them, I'll try and make sure I um, don't forget the others. Quantum vacuum energy is another. The as yet unsolved coupling of the fundamental forces, bringing gravitation into the understanding with the electromagnetic forces. Um, Looking at the cosmological phenomenon of what's called dark matter and dark energy. So those are all some things. Physical evidence for negative mass or negative energy states. So those are some of the ones. But to come back to inertial induction and Mach's principle, many of you are probably aware of the concept of inertia, that you have to push on an object to get it moving, and then once it's in motion, its own inertia wants to keep it in motion. But the part you never think about, or that you seldom think about, is that, well, it's not just a property of the mass, it's a relationship between the mass and the surrounding space-time. If I were to rotate this room, and you might not be able to tell if the camera's fixed to it, but if I had a bucket of water here and it was rotating, the water would go up the edges. But from the still camera, it doesn't look like it's rotating. So what is it about the nature of space that allows for accelerations to induce forces? Where does that come from? Mach's principle, the idea is that, well, it comes from all the surrounding matter in the universe, that you can't have motion unless it's relative to something else. And there's about 20 attempts to advance Mach's principle into equations that can be tested. Some have been dismissed, some are still open, and it was hoped that Einstein's general relativity would be able to incorporate it. It didn't. Now that notion has morphed into a term called inertial induction. Is there something about the properties of space-time which induce the property of inertia to show up, and what might that be? There's been hypotheses that it has to do with vacuum energy, and some of them have not worked out. The math got into some things where those specific ideas didn't, but that idea in general is still open. And for those of you who don't know what quantum vacuum energy is, the simple way to explain it, and there are multiple ways of explaining it, is in the uncertainty principle, when you can never get down to absolute zero of anything. One interpretation of it is that if you have a space and you remove all the matter, all the energy from that space, there is still some virtual energy there of half a photon. And if you add up all the possible frequencies of that energy, and electromagnetic energy is the one that's usually done for, you can get mind-boggling amounts of energy densities higher than the density of a proton, depending upon what you pick as the upper cutoff frequency of the radiation. And one of the experimental hypotheses of this, if you have a couple of conducting plates which eliminate longer wavelengths than the ones that can fit in between the plates, and get them close enough that eventually the very few allowed states in between are much less than all of those states and all of the longer wavelengths outside, and the plates will be forced together. And the experiments to measure that and predict those forces are on par with each other. And there has been a theory of, if you move a mirror in an asymmetric way, that you can take these virtual photons and convert them into real photons and then have a photon rocket. It's an extremely inefficient photon rocket, and photon rockets aren't that great in the first place. But like in principle, okay, you can create thrust to it. And there's unfortunately on these really sensationalistic or these edgy subjects, there can be a lot of sensationalist work that jumps to conclusions and can do things sloppily. And unfortunately on all these, there's been some of that. One way that you can, when you're coming across these things, that you can filter these out, is that if the work is being very careful to describe their results and their methods and trying impartially to find out if something works or how, that's a stronger work. If the work already concludes that this is the best idea we have and they only give you promotional material, no. And also, if they say this is impossible and here's the one reason why, those aren't all that useful either. You need that middle ground, and you do need the critiques. In other words, if someone says it's like a thruster's impossible because it violates conservation of momentum, that takes you to the next level of detail. Well, how is it satisfying conservation of momentum, or where might those be special cases? And there are some things that have been under test for a few years that do appear to be misinterpretations of vibrational effects, but they were rooted in some of these unsolved questions of inertial frames, where you could get a propulsive effect and it didn't violate conservation of momentum, even though on the surface of it, it looked like it did. You can run into those cases too. So watch out for the impartiality and the carefulness of the work. If they seem impartial and careful, you can pay attention to them. If they seem sensationalistic or too much salesmanship or too much pedantic disdain, yeah, then skip those. Okay. Let's see if we have any other questions. Okay. The challenges with the Interstellar Flight. I don't know how much you know about those. If you've heard of Breakthrough Starshot, the idea is to use a 100 gigawatt laser array in the southern hemisphere, firing onto a 4 by 4 meter light sail whose total mass is 1 gram. That by those numbers, you should be able to get that up to 20% light speed, and that thing could fly by our nearest neighboring star in 22 years. And somehow, with its 1 gram mass, it could optically send back the data or an image, and it would take 2 years because of the low data rates to send that image back. Prior estimates said 20 years. But that's one concept that doesn't violate the physics that we know, but the engineering things are daunting. There's ideas for fusion rockets. There are ideas for space drives that are at the either where someone has an experimental test or experimental device, and those have been under test. The ones that I know about, the EM drive, the Mach effect thruster, are apparently attributable to other causes, but who knows if we might find something. And that's what I got.
Well, thank you very much, Mark. That was a great talk. People seem to really appreciate it. Now, are you going to be able to join people over on the Discord chat?
Oh,
Auditorium even?
I can certainly take a look at that. Which of the things on Discord would I go look up?
Okay, so it's NASFiC Columbus